before discussing the sinusoidal oscillators, I like to give you extend the feedback amplifiers, the discussion on feedback amplifiers to an operational amplifier example. After that, I'll come back. I'll discuss about the oscillators. Please look at this picture. So this is an example for voltage series feedback using an op-amp circuit. So here this is an operational amplifier. It is an amplifier with very high voltage gain and very high input impedance. Ideally the input impedance is infinity, and very low output impedance. The output, that means the output impedance ideally should be 0, and voltage gain is infinity. Then please note that a fraction of the output voltage, and the fraction is R2 by R1 plus R2. So therefore beta is equal to minus R2 by R1 plus R2, because so this fraction is applied to the negative terminal, and the operational amplifier is basically a difference amplifier. The output voltage is an amplified version of this voltage applied to the positive terminal minus the same gain times this voltage. Voltage series because it is voltage feedback, because output voltage is tapped, and it is applied in series to the input signal is Vs greater than 1. So we know that this is approximately equal to 1 by beta, and that is equal to, in this particular example, minus R1 plus R2 by R2. So this is the gain of the operational amplifier here. So this is an example for feedback, voltage series feedback, and it is an op-amp circuit. And I will give you another example. This is for voltage series, and I will give you a circuit example for current series feedback. So this is the example. I am giving an example of a transistor circuit. So the output is taken here. It is a common emitter configuration, and this is for the sake of biasing. So this is the coupling capacitor to couple the input signal to the amplifier, and this is the output. And this is the collector resistance, as I mentioned, this is the biasing resistance, and this is Re, a feedback resistance. And this is the output voltage. Is it voltage feedback or current feedback? If I tap the output here and directly feed and apply a current or voltage at the input by tapping the output voltage, it would have been a voltage feedback. But please note that the feedback is proportional to the output current. Please note that a voltage of amount equal to Vf is being fed back in series with the input. The base to emitter potential here is the input minus Vf. Therefore, that Vf is appearing in series with the input. So definitely it is series feedback. And the feedback voltage, it is not directly derived from the output voltage, whereas it is derived from the output current, because the current that flows through the collector here, almost the same current flows through the Re also. Hence, the feedback quantity is a voltage which is proportional to the output current. Vf is equal to the output current into Re. So, that much of voltage is being fed back in series with the input voltage. Therefore, it is current feedback, hence it is current series feedback. If the output is taken here, if this is the output voltage, like in the previous example which we discussed in the last class, then it would have been a direct voltage feedback, voltage series feedback. Now, the current is, the output voltage is this and not this one, and this Vf is proportional to the output current, hence it is current series feedback. Now, we shall discuss about a new topic which is also based on the principle of feedback. So, that is sinusoidal oscillators. So far, we have been discussing about two-port networks where we apply an input and at the output we get an amplified output. We get an amplified signal at the output. Whereas now an oscillator is a one-port device and it has therefore only one port, and between these two terminals of the port, it gives you some oscillatory voltage, a voltage which oscillates with time. And if this voltage variation is sinusoidal, it is a sinusoidal oscillator, and if it is a square wave, it is a square wave oscillator, and so on. That means the voltage here is a function of time. So, it is V sin omega naught t, where omega naught is the radian frequency of the waveform, radian frequency, which is equal to 2 pi into f naught, the absolute frequency, and V by square root of 2 is the RMS voltage of the sinusoidal output, whereas V is the peak voltage and 2V is the peak to peak voltage. So, in an oscillator, when an oscillator is specified, we specify the oscillator in terms of the frequency and the RMS output. And another very important parameter here is stability of the frequency. Because of various factors, this frequency varies slightly with time. If you measure it at 11 o'clock, if it is a 10 kilohertz oscillator, it may give you 10 kilohertz frequency. And at 12 o'clock, it may be 10.00001. The frequency may slightly change. If the frequency stability is very high, then we call it, if the frequency is constant with respect to time or the variation is very low with respect to time, we say that the oscillator is a highly stable oscillator. And in general, so the frequency of the oscillators change slightly. It may be 1 part per million or 1 in 10 to the power of 8 cycles or of that order. So, it means that the variation is of the order of say 1 hertz. In 1 megahertz, it's the variation is plus or minus 1 hertz. If you say that it is 1 ppm. And the oscillators are applied in various fields. Many electronic circuits use oscillators, counters use oscillators, the timers use oscillators, Your power supply is an oscillating waveform to reduce the losses, and for communication modulation purposes we use oscillators, and in various other circuits also we use oscillators.
So, the signal generator we use in the lab, does it work?
So, here is a question. Yes, the signal generator you use in the laboratory is an oscillator. It gives you an oscillating voltage. It's an oscillator with, it gives you a few functions like sine wave, square wave and triangular wave. Some of them give you sine wave and square wave, and the frequency is variable, amplitude is also variable. So, that is a function generator and it uses oscillator inside. It uses an oscillator inside. So, there are many applications, and as an example let me take the wall clocks and the watches. You have a stable oscillator, quartz oscillator inside a watch. Why do you need that? So, if you do not use a highly stable oscillator, and if its stability, instability is 1 ppm, please note that for every 1 million seconds there may be 1 second error. So, it may appear to be a very high figure, but if you use this watch and without setting, if you want the watch to work without correction, please note that after years also the error should be within a fraction of a second. So, that is the order of accuracy we need. Therefore, we need highly stable oscillators. Now, the question is how to produce these oscillations. If you view this oscillator as an amplifier, there is no input being applied and it is producing an output. It is creating an output, sinusoidal output. How is this possible is the question. So, we have oscillator circuits available using which we can generate this kind of oscillations, and an oscillator is a feedback amplifier. Basically, an oscillator is a feedback amplifier. Now, let us discuss about how oscillations can be produced. Now, let us consider an amplifier. This is an amplifier with gain A, and say there is a feedback network beta, and a feedback voltage is applied to the input and it is added to the input, and this is a switch. In this kind of arrangement, because of some reason, if you produce a one cycle of a waveform here, so you input one cycle of a sinusoid into this amplifier and open the switch, and the amplifier amplifies it, amplifies the signal. The voltage is a strong voltage, and say it has some delay also involved, and this voltage is now multiplied by beta, and what you get here is again a similar voltage cycle. And let us assume that there is some delay, one cycle delay that takes place in between the input and output. So, when this goes to the input, and if the feedback is positive, and if I open the switch now and do not allow any other input, can this feedback voltage sustain the output? Now, one cycle has gone and it has come back here, and here I remove this, I do not apply the next cycle, but this cycle which has come back acts as an excitation for the next cycle, and the second cycle will be produced. And this second cycle after some delay goes here, gets added, there is nothing here to get added. So, this is applied to the input and a third cycle is produced. This way these oscillations can be sustained. And the amplitude will remain equal or constant if A beta is 1. Magnitude of A and beta, if it is 1, then please note that whatever goes here into this, the same amplitude, whatever goes here will be returned here, amplitude will remain the same. Hence, the output oscillations will remain at a constant voltage. And please note that this delay has to be of 1 cycle or integral number of cycles. It should be 1 cycle here. Now, let us consider another alternative. You produce a fraction of this voltage. You produce a small fraction of this voltage waveform at the input. And after a short delay, after this much delay, say this is delta duration. Let me draw this diagram in an expanded one. Now, let us say at the input we generate this much fraction over a delta time. So, we generate this much waveform, and within delta time it gets magnified and again attenuated by beta, and it comes back to this place. So, it will make up this part and this one will make up this next part. And when this delta is very small, please note that the input voltage and output voltage is almost same except for minor difference, and in which case also the oscillations can be sustained. It produces the waveform. Now, in general, the amplifiers have some frequency response, as I mentioned earlier. Therefore, it is not exactly A, but it is AF. And beta also can have some frequency response, is frequency dependent. If it consists of capacitors and inductors also in the circuit, then beta also varies with frequency. Okay. So, in general, therefore, A and beta are functions of frequencies. Now, if you want the magnitude of A beta to be 1 and angle of A beta to be n times 360 degrees, because then only oscillations can be produced, and if this is so, and these two conditions are to be satisfied at a particular frequency, and when these two conditions are satisfied at a particular frequency, oscillations are produced at that frequency. Say the condition is satisfied at 2 kilohertz, and if you apply a 1 kilohertz waveform here and remove it, it cannot produce 1 kilohertz waveform, because the sustaining conditions are not satisfied. A 1 kilohertz waveform may get attenuated if A beta is smaller than 1. In the next cycle it would be with a smaller amplitude than the previous one, and the following output will be much smaller than this, and therefore it dies down as a transient. Output does not get sustained. Therefore, only when A beta, magnitude of A beta equal to 1 and angle of A beta is equal to n into 360 degrees is valid at a particular frequency, oscillations are produced at that particular frequency. And this criterion or these two conditions are known as Barkhausen criterion. I repeat, the conditions are: the loop gain, this is known as the loop gain, is the overall gain from one point to the same point along the feed forward and feedback path. So that is known as loop gain. So magnitude of the loop gain should be unity, and the phase shift or the angle in the loop of the loop gain should be n into 360 degrees. Why should it be a multiple of the cycle? As I mentioned, for oscillations to be produced from a small disturbance, so if the next disturbance has to be produced, it has to be a multiple of 360 degrees, or from one cycle the next cycle has to be produced, it has to be a multiple of 360 degrees. So this is known as Barkhausen criterion, and the Barkhausen criterion can be satisfied only at one particular frequency, because AF is a gain is a function of frequency and beta is a function of frequency, and it is sustained at only one frequency. It is valid, the conditions are in general valid at only one frequency. Now, therefore, what we need is, in an oscillator, we need an amplifier with some gain A, and a feedback network with some gain beta, and we should see that, so A into beta is equal to unity, magnitude of that is unity, and angle is n into 360 degrees. So when we design an amplifier, what we do is we use a phase shift network for beta and see that the overall phase shift is a multiple of 360 degrees. And you have seen that some amplifiers, like a common emitter amplifier, gives you a gain which has a negative sign. That means the amplifier itself is creating a phase shift of 180 degrees in the signal. If the input signal is like this, we get an output signal which is like this. That's why the gain is negative, or there is a phase shift of 180 degrees. If there is a phase shift of 180 degrees created by an amplifier, then you should design your feedback network such that it offers the remaining 180 degrees, so that the loop gain is 360 degree. Loop gain this loop has a phase shift of 360 degrees. Hence, we go for a phase shifter network for the feedback path, and an amplifier, typically a common emitter kind of amplifier for the designing the amplifier. Now the next question is, how do you generate oscillations? Is it that really we use a function generator and then use a switch and apply a fraction of a cycle into this oscillator circuit and then shut the switch off? It's not necessary really. All amplifiers do produce some amount of noise within them. And now let me discuss about how oscillations are produced to start with. Initiation of oscillations or production of oscillations. If you look at the collector current and plot the collector current of an amplifier, say the amplifier is designed to produce 1 milliampere of collector current. So a collector current looks like this. But if you really look at it microscopically, so you will find that there is fine variation, noisy variations in the collector current. It's not that exactly, so that many charged carriers pass through the carrier junction for every second. Can we guarantee that only that many number of charge carriers pass through the collector junction every second, so which can make a 1 milliampere current exactly. So it is not so. So there is a fine variation, it is a random phenomenon, and there is a fine variation in the number of electrons or the holes that pass through the collector junction every second. Hence, if you look at it microscopically, so you will find that the collector current has a fine current variation. Now, this can be equated to a constant current plus some random variations. And if you look at the frequency components of the random variations, you find that all frequency components are available in the random variations. If you find a spectrum, power spectrum or Fourier transform of this kind of random variations, you will find that all components are possible. So, since noise is present in amplifiers, although it is very small, since noise is present in the amplifiers, please note that the oscillations you require to produce a high voltage, moderately high voltage oscillations are already present in an amplifier itself. Therefore, at the base of an amplifier or at the input of an amplifier, you can always find some small voltage, microvolts or nanovolts of random voltage at the input, which gets amplified to the, and you get an amplified noise at the output, and this gets further attenuated by beta, and so this one gets added to the input. Now, if A beta is slightly larger than 1, say A beta is 1.1, and if this is to start with, it is, say it is 1 microvolt, so in the next instance it will be 1.1 microvolts, and in the second instance instead it will be 1.1 squared, 1.1 cube, and as a result the oscillations are initiated and the oscillations go up geometrically. In the present example, so it goes up with time as 1.1 to the power of time. So oscillations are produced, and the oscillations amplitude rises. If A beta is slightly larger than 1. If A beta is exactly equal to 1, then oscillations cannot be produced, and you have the noise only, so that is passing. Now, if A beta is slightly larger than 1 to start with, then the oscillations build up, and after some time you find that the oscillation amplitude rises up to certain level, and if it further goes beyond the VCE of the amplifier, can the output voltage go beyond VCE? What happens to the output oscillations? So they get distorted, either they get saturated on the lower end, and they get saturated, the transistor becomes cut off, and the output can rise only up to VCC on the outer side. Now, can the amplitude further go up? So amplitude cannot further go up. So once it goes into the nonlinear region, please note that if you plot the characteristics Vi to V0 characteristics of an amplifier, so it has a nonlinear characteristic something like this, and the slope of the amplifier gives you the gain, and once it rises beyond certain level, input rises beyond certain level, the output is less than the gain times the input. Output does not rise output tends to remain constant even if the input is increased, and as a result the gain becomes lower than what it was for low amplitude signals. Hence, the moment the signal enters the nonlinear region, the gain gets lowered automatically, and at certain amplitude level A beta will be equal to 1, and the oscillations, the build-up of the oscillations stop at that particular amplitude, because at that particular amplitude level the A into beta is equal to 1, and the oscillations are sustained from that point onwards, and you have constant amplitude oscillations. This is how oscillations are produced to start with, and oscillations are sustained. I repeat, the oscillations can be generated or produced to start with because of the noise present in amplifiers, and this noise has all frequency components in it, and only that component for which A beta is equal to 360 degrees or a multiple of 360 degrees, only that particular component, sinusoidal component or monofrequency component, returns in phase, and if A beta is slightly larger than 1, and at that frequency the amplitude builds up, and after some time the amplitude rises up to, after at some transient time the amplitude rises up to certain level, and at that level the gain goes down slightly and makes A beta equal to 1 exactly, and the oscillations are sustained at that particular amplitude. And this is possible for only one frequency, because this is a frequency sensitive network, this is also a frequency sensitive network in general. So only for whatever frequency, so the condition for oscillations, the Barkhausen criterion, is satisfied, only that particular component out of the noise builds up and the oscillations are produced at constant amplitude there. So therefore the frequency is decided by the phase shift network. So we see at what frequency A beta is equal to unity.
Sir, in may vary. So leaning to 360.
Right.
So there may be a number of components which will be in line with that.
Yeah, your classmate has a question there. N may vary, and if for one frequency the phase shift is 360 degrees, there may be another frequency, it may have a phase shift of 720 degrees, and oscillations can be produced there also. But please note that the networks A and beta are frequency sensitive, and they have different gains and different attenuation at different frequencies, and that A beta equal to 1 is also satisfied only at one frequency out of these two. So if so, at that particular frequency only you will find oscillations sustaining.
So what difference there exists when A beta is -1?
If A beta is equal to -1, naturally the oscillations do not get added in phase at the input, and you won't get oscillations at the output. You will only find some small amount of noise which is microscopically visible, so only that noise will be present at the output.
Sir, but the criterion says that mod A beta should be 1.
Yes, and the second criterion says that angle A beta is a multiple of 360 degrees. Mod A beta equal to 1 and angle A beta is equal to 360 degrees, a multiple of 360 degrees. Or it can be stated as a single condition, A beta is equal to 1.0 plus J0.
So that means that there is a unique value of n per circuit.
Right, certainly.
So practically what is the rising time of the amplitude?
So there is a question there. Normally, what is the amount of time a circuit takes for oscillations to, for what is the transient duration after which the oscillations are sustained? Well, you tell me the question, you give me the answer. It naturally depends on magnitude of A beta. If A beta is equal to 1.05 as case 1, A beta is equal to 1.1, A beta is equal to 1.2. And what is the component of that particular sinusoid to start with? So these factors decide. If A beta is larger than 1, highly larger than 1, say it is like 1.2, it builds up very fast.
So what is the order?
So it is of the order of a few microseconds. It depends on the, it runs into milliseconds, because usually this beta network is a narrowband network, and the transient response is large, and the because of which reason it takes some time. If the time constant, the dominating time constant of beta is say 1 millisecond, within 5 milliseconds, 5 times the time constant, so oscillations can build up to about 98 to 99% of the time. So it depends on the bandwidth of this beta network, and obviously A beta also. Now let us consider different amplifier circuits which can be used for the production of oscillations, and different the feedback networks for which can be used for producing oscillations. So there are different kinds of circuits possible. One popular circuit which is used for low frequency oscillations is a phase shift oscillator. It uses an amplifier, either a transistor amplifier or an op-amp amplifier, with typically negative gain. So A is negative. Therefore, out of A beta, 180 degrees of phase shift is already here. And to produce the remaining 180 degrees phase shift, one can use an RC network. And how many RC sections are needed to produce 180 degrees of phase shift? Each RC segment can produce a phase shift of at the most 90 degrees phase shift. And when it produces 90 degrees phase shift, the attenuation is, for example, take this section CNR. If you want 90 degrees phase shift here, R should be 0. So only when R is 0, it produces 90 degrees phase shift. Please note that with that, the disadvantage you have is the attenuation is infinity. So if each section produces 90 degrees phase shift, with 2 sections itself you can produce 180 degrees, but beta would be 0 in that particular case, and A has to be infinity. So we have a difficulty with this. Hence, typically we go for a 3-section phase shift network, with each section producing about 60 degrees of phase shift. And with 60 degrees of phase shift, we have no problem, the attenuation is not bad. And then you apply the feedback voltage to the amplifier. It is not necessary that all R's and C's are equal here. You can see that one section gives 70 degrees, another section 60, and another section 50 degrees of phase shift. There is no harm. But the design becomes simpler if they are of equal values. if they are of equal value. Therefore, a 3-section RC phase shift network is used to produce the remaining 180 degrees of phase shift. And this is an amplifier with gain A, and A is negative. Now, if you analyze this circuit, produce the phase shift between input and output, okay, analyze and then find out at what frequency it produces a phase shift of 180 degrees. So, you will find that that frequency is equal to 1 by 2 pi RC into square root of 6. At this frequency, the phase shift is 180 degrees. This is as far as phase shift is concerned. And we have another thing. So, this is the output voltage exciting the feedback network. This is the feedback voltage. What is the ratio between the feedback voltage and the input? That is, how much is beta in this particular case. So, in this particular case, at that frequency, beta is equal to 1 by 29. It can be mathematically analyzed and it can be shown that, so these two are the conditions. Now, coming to the amplifier design, if these are the outcomes of a phase shift network, now you have to select an amplifier. And if the amplifier has negative gain, and what is the gain of the amplifier now? The gain requirement? Gain should be greater than 29, should be slightly greater than 29, gain should be, because beta is equal to 1 by 29. To satisfy mod A beta to be A beta equal to 1, you need A to be slightly greater than 29. So, this is how an RC phase shift network can be designed. You have to use an RC phase shift network for 180 degrees phase shift with these values equal in each section. The frequency at which it gives 180 degrees phase shift is 1 by 2 pi RC in square root of 6, and at that frequency the feedback factor beta is equal to 1 by 29. Hence, you have to design an amplifier with gain slightly greater than 29. So, this can be an op-amp circuit and design this phase shift network, and it acts like an oscillator. So, it produces oscillations with constant amplitude at the output. If A beta is much larger than 29, significantly larger than 29, maybe 35, 40 or something like that, then please note that the oscillations have to go deeply into the saturation and cutoff. The amplifier has to deeply go into the saturation and cutoff to reduce the gain such that A beta is equal to 1 for sustaining oscillations. Then the output you get is a distorted output like this. If you want neat sinusoidal oscillations, so you should see that A is slightly greater than 29, in which case the oscillations would be so like this. The moment it barely enters the nonlinear region, A beta should be equal to 1, and that's possible when A is almost close to 29 but slightly greater than 29. Now, I will give you an example of a transistor circuit. So, if we use a common emitter amplifier and the gain has to be larger than large, hence you have to use a bypass capacitor here, and the amplifier circuit I am using here is with self bias. This is a self bias common emitter amplifier circuit, and to have sufficiently high gain, so we have bypassed with a bypassed the emitter resistance with a capacitor, and this is the output, and here is the input. Now, we do not require an additional coupling capacitor because this RC network has a capacitor here, and this capacitor itself acts like a for blocking DC also. And here we need a blocking capacitor. So, this is an example for a transistor phase shift oscillator. Transistor RC phase shift oscillator. It is also possible that this resistance can be made to be a series resistance here, in which case we can avoid this coupling capacitor, and a few variations are possible in the circuit. And please note that in this RC here, the input impedance of this amplifier is coming in parallel with this R, and because of which this phase shift varies. This phase shift is different from the other sections. Okay. So, you have to see that this Ri in parallel with this makes that particular R in the case of an RC phase shift oscillator.